Good morning, everybody. My name is Terry Donovan, and I just want to ask Sky if you can hear me.
I can hear you.
Okay, perfect. Well, thank you for coming today under these circumstances. We're here to hear Sky Pearman-Gillman give her defense of her dissertation. And I'm one of the lucky co-advisors of Sky, and I'll just give you a quick little bit of a background and then pass you over to Jed Murdoch, who is a co-advisor. So Sky earned her bachelor's degree from the University of Washington, and a fun fact that I love is that she was on the rowing team. So for you boys in the boat fans, it's a great connection. Sky came to the University of Vermont as part of a large McIntyre Stennis program that was headed up by Jen Pontius. And Sky was the sole wildlife contingent of that project, and as I mentioned, is co-advised by me and by Jed Murdoch. And the overall goal of that project was to explore how changes in forest ecosystems with land use and climate change will affect different wildlife species. And you'll see that Sky tackled 10 wildlife species that are really highly visible in the public eye. They're harvested species. And you'll hear how she approach this, this problem of how do you predict how wildlife will change in the future by using expert elicitation methods. So I'd like to just formally acknowledge that a large number of state biologists and federal biologists and others contributed to this work by providing their expertise in the form of a survey. I'd also like to fully acknowledge Matthew Duvenek, who played a critical role in the second two chapters of Sky's dissertation by providing the scenarios for different alternative futures. And I think Matthew's here, and Matthew, thank you for joining us today.
Delighted.
Great. I also want to just give you a quick introduction to Sky and how Sky came to be at the University of Vermont. She came recommended by Chris Grew, who is with the Washington Cooperative Fish and Wildlife Research Unit. And if my memory serves me right, Chris reached out to Donna Parrish and said, we have a fantastic person here who's looking for a PhD program. And Donna then it trickled over to Jed and I want to read just a quick excerpt from Chris's letter of recommendation, because this really says it all. So he says, this is in his letter to us to recommend Sky to the program. Sky is a truly exceptional candidate for your program. She's demonstrated to me and others all of the qualities you would desire in a graduate student: bright, adaptable, conscientious, attentive to detail, prompt, hardworking, great work ethic, great personality, pleasant, ability to work alone and with others, confident but able to ask questions, multitasks, well-spoken, and writes well. Sky's work will exceed satisfactory. It will be outstanding. And those are incredible words. And of course, when we got this letter, we're like, oh, we better look at this candidate. And that's really basically how Sky ended up here. And I'll just say that she's been all of those things. She is an incredible person to have worked with, and she's done an amazing job on a project that really was extremely lofty and without really concrete objectives. And we had to take this big, lofty goal and turn it into some products, and Sky's done an outstanding job. I also just want to say hello to Sky's family. I know that I'm looking at the participant list and I see quite a few people with the last name of Logan, and I just want to say welcome. And this is a big day for you as well as for Sky. So with that, I'm going to pass it over to Jed Murdoch, who's a co-advisor for Sky. And I'll just quickly say, though, that we'll have a chance for questions and answers at the end of Sky's presentation. And if you have some questions, just put those in the chat, and then Jed and I can monitor the chat and call on people after the presentation is over.
Great, Terry. Thank you very much. That's a really nice introduction. I will not say too much more. Again, my name is Jed Murdoch. I'm a faculty member and currently serving as chair of the Wildlife and Fisheries Biology program at the University of Vermont. I guess I would really just echo the fact that this project did start with some big, lofty goals, and in some ways it was sort of a blank slate. And over the course of, Sky, correct me if I'm wrong here, about 4.5 years, you took some general goals and turned them into a really dynamic dissertation that expanded the scope of the project beyond Vermont, across all of New England, that plugged into Matthew's group, that allowed you to project or develop some products that evaluated conditions for species across multiple futures. So we're really just impressed by your ability, your capacity to take these general goals and really make something of it. So I would say congratulations to getting this point. This is the final step and really a capstone to 4.5 years of really hard work. And we've just been really impressed. With that said, let me also just make a quick note to thank the committee members who've been a part of this as well. Dr. Tony D'Amato, who's chair of UVM Forestry, is a member of the committee, along with Dr. Ruth Mickey, who's from the Department of Mathematics and Statistics. So welcome to you both as well. All right, with that said, Sky, let me pass the ball to you.
Great, thank you. Wow, thanks both Jen and Terry. That was a really wonderful introduction, so I appreciate that. And hello, everyone. Thank you for joining us remotely today. Obviously, this is not the ideal platform for a dissertation seminar, but we are doing the best given the current situation, and I appreciate you all tuning in and joining us remotely. So today I will be talking about my dissertation research, which is broadly focused on understanding how changes in climate and land use will impact the future distribution and spatial resilience of wildlife species in the New England region. So let's see if we can get my slides to work. There we go. All right, so I'll start off with a little bit of background or broader context for this research. As we all know, climate and land use patterns are changing worldwide, and those changes can have numerous ecological and economic consequences within different regions. So my research is focused on the New England region, and this region is currently one of the most densely forested and heavily populated regions in the United States, which make it both an economically and ecologically important region. Unfortunately, this region is also undergoing relatively rapid changes in climate, land use, and land cover. So as these changes increase in the future, shifts in climate and land use may have considerable consequences for our wildlife species. So my research is focused on wildlife within this context, and it aims to better understand how future changes here in New England will impact our regional wildlife. So in order to improve our understanding of wildlife futures, this dissertation is focused on 3 main studies. Our first study, or our first chapter, is focused on understanding where species occur within our regional landscape, and then using that information to develop these predictive tools or these species distribution models. Our second chapter is focused on distribution change for our wildlife species. And in this study, we use our models to understand how projected climate and landscape conditions will impact our species' future distribution. And we also evaluate how influential drivers of landscape change impact distribution for our wildlife species. And then our third chapter is focused on species resilience and land protection in New England. And in this study, we identify areas where species are likely resilient to future change, and evaluate trends in our species spatial resilience and existing land protection. So these are the 3 studies that I'll be talking about today. These 3 chapters are they're quite cohesive, with both chapters 2 and 3 building off of the results and the elements that are developed in the previous chapters. However, each chapter does address its own research questions and has different objectives that it targets, and I'll highlight each of those as I talk through these studies. So we'll start with chapter 1, which is focused on the development of our species distribution models. So this chapter has 4 main objectives. The first objective is to develop a regional multi-species survey that we can use to collect our species-specific probability of occurrence data. Our next objective is to then conduct that survey using expert elicitation methods, and then use the data we collect through that survey to develop our species-specific distribution models. And then finally, we can use those models to map our species' regional distributions. So I'll talk through each of these objectives briefly, starting with a little bit of background about how we collected our data and how we developed our models. So as I mentioned, we used expert elicitation to collect our species data. And we collected that data for 10 different focal species. So those species pictured here are our focal species we're working with in this project. So these are all game species or harvested species in the New England region. These wildlife bring in revenue for management agencies and are a large focus of wildlife management programs. So we want to focus on developing tools for this subset of our regional wildlife. So in order to develop distribution models for these species that are both regionally applicable and spatially compatible, we needed a large amount of uniform or cohesive data. Unfortunately, distribution data are lacking for many of these species, especially at this regional extent. And what that meant for us is that we needed to collect our own data. And we collected that data through expert elicitation. So what this means is that rather than me going out and collecting data through observational field studies all over the New England region, I was able to elicit the help of wildlife experts to collect this data. And how we were able to elicit their help was through the use of a virtual wildlife survey. So we used the AM survey application that was developed by the Vermont Co-op unit to design a versatile survey that allowed experts to select the species and regions in which they had expertise, and then only provide feedback associated with those selections. So that versatility is what really simplified and standardized our data collection, making it possible for us to collect a large amount of data for multiple species at this regional extent. So for our data collection, experts would log into the survey application. They would select the species which they have expertise from this list on the left, and they would select the states or the regions in which they have expertise. And then they would complete these virtual site surveys. So experts would be given 30 randomly generated survey sites from within their selected region, and they'd be asked to use the information provided about that site to make an estimate of how likely their target species is to occur in that location. So to help them with this estimation process, we provided experts with 3 main sources of information. The first main source is this functional Google Map image here. And they also were provided with this variable table and these land cover and forest composition tabs. And all this does is it provides them with detailed information about the location and habitat quality of that survey site. Experts then use that information to make a judgment of how likely their focal species is to occur in that site, and then they can adjust these probability of occurrence and these confidence sliders to indicate that estimate. So these probability of occurrence measures are what we recorded for each species and site throughout this survey process. So this survey allowed us to collect a large amount of data. We were able to collect 3,576 occurrence estimates for our 10 wildlife species. And we were able to collect that over 1,152 unique survey sites throughout New England. We collected this data in about a 3-month open survey period. And for those of you who are familiar with observation or field-based studies, collecting this level of data for a size of a region as New England and for 10 different species, that's something that would not have been feasible in that time frame without the use of expert elicitation. So all we're seeing here on this figure is just a breakdown of the data we were able to collect through that survey, with the number of survey responses on the y-axis that we were able to collect for each of our species. And that's just broken down by the state in which we were able to collect that data. So once we had this data, we could use it to develop our distribution models. So these are the models we developed for our 10 focal species. All these models were developed using mixed model methods where our experts and our sites were considered random effects, and our habitat covariates, such as these ones shown here, are our fixed effects. So this modeling approach, it allowed us to identify the variables that are most influential on our species distribution. So the example we're highlighting here is for American black bear, and we see that these variables shown on the bottom, those are the variables we isolated as the ones that were most influential in driving that species distribution here in New England. We also were able to calculate an effect size associated with each of these variables. And this is the information, these scale variables and these directional coefficients that we could then use to estimate and map our species distribution. So a quick side note, for time's sake throughout this presentation, I'm going to be using American black bear as an example species. So anytime you see this little black bear image in the corner, just know that the results you're seeing on the slide are associated with that species. However, we did conduct the same methods and have produced similar outputs for all 10 of our focal species. So continuing with our black bear example, to map our species distribution, we can take our distribution model for that species, as well as the spatial land cover data for our region of interest, and we can apply our model across that landscape to estimate our species regional distribution. And what we're seeing here is a distribution map for black bear, where our red regions are areas of high occurrence probability and likely favorable habitat conditions, and those blue regions are areas of low likelihood of occurrence for that species. So this process was conducted for each of our focal wildlife species, giving us these regional distribution maps for all 10 species. Again, here we're seeing a high probability of occurrence in those red regions and a low probability of occurrence in those blue regions. So as we can see, there is a lot of variation between our species. And that's something we expect because a lot of these species have quite different habitat requirements. We're also seeing that some of our more generalist species like coyote or white-tailed deer, we're seeing a lot of red in those maps. So we're seeing pretty high likelihood of occurrence throughout much of that region. While other species with more habitat constraints like gray fox or moose, we're seeing that there's lower levels of regional occurrence. We also calculated distribution statistics from these maps to look at regional and state-based trends. So here we are seeing our average occurrence likelihood for our species on the y-axis, and that's broken down by state on the x-axis. We also have these regional average, the regional average shown in these gray dotted lines. So really the main takeaway from this graphic is that we see a lot of variation among our species. We see that the regional averages are quite different among our species. We also are seeing that different states have quite different averages as well. So moose is a perfect example of that, where we're seeing high probability of occurrence in Maine and quite low probability of occurrence in Connecticut. So this is potentially valuable information for both state and regional management. These models and these maps, they provide these comparable statistics among species within our region as well as states within our region, and that can be useful. So we also combined distribution information across our focal group to look at trends in our focal species richness. So what we're seeing here on our map is red regions are indicating areas where multiple species are likely to occur, and those blue regions are areas where there's a low likelihood occurrence for most of our focal species. Generally, we're seeing that most of the region has relatively high species richness for our focal group, and that's leading to a regional average about 7.16. Given that this is on a scale between 0 and 10, we're seeing pretty high levels of species richness for our focal group throughout this region to get that value of about 7. We do, however, see that if we look at our state-based statistics, our more developed states like Connecticut, Massachusetts, and Rhode Island, we're seeing that there's lower levels of species richness in these states, and also higher variability in those measures. And this is worth noting because this may be an indicator of something that we'll see throughout more of the region in the future if land use changes continue and we see more development expansion. So that brings us to the end of chapter 1. This study, we developed our expert elicitation survey. We used it to collect that regional occurrence data for our focal wildlife species, and we used that data to develop our distribution models and then mapped our species' current distribution for our New England region. So as I mentioned in the beginning, chapter 1 really lays the foundation for our following chapters, and the rest of this work, it targets the same region and the same focal species and uses our distribution models and current distribution maps to address questions about future change. So moving on to chapter 2, which is focused on evaluating the drivers and consequences of distribution change. So this chapter has 3 main objectives. The first objective is to map our species' future distributions relative to projected climate and landscape conditions. We can then evaluate how alternative landscape futures and drivers of landscape change influence our species distribution change. And then finally, we can identify which drivers have the greatest influence on distribution change for our focal wildlife. So in order to conduct these future distribution assessments, we needed information about how the New England landscape may look in the future. And this led us to our collaboration with the New England Landscape Futures Project. For those of you who are not familiar with this project, the NELFP, or the New England Landscape Futures Project, is led by Harvard Forest Long-Term Ecological Research Program and the Scenario Services and Society Research Coordination Network. And this is a research group that has developed these 5 different scenarios that forecast how the New England landscape may change over the next 50 years. So they project how this landscape will look by the year 2060. So these scenarios are built around 2 high impact and highly uncertain drivers of landscape change, which are natural resource planning and innovation on the y-axis and socioeconomic connectedness on the x-axis. And what this means is that this research group has forecasted how these different levels of natural resource planning, innovation, and socioeconomic connectedness, how they impact trajectories of development, agriculture, timber harvest, and conservation throughout New England. So I know there's a lot going on in this figure. So let's just look at a single one of our scenarios, the growing global scenario down here. And I'll give you a better idea of what's driving these projections and how we're using this information for our assessments. So the growing global scenario is built around a low investment in natural resource planning and innovation and a global approach to socioeconomic issues. And what this means is that there's a narrative that's driving this scenario, and that narrative states that in the future, New England will experience inefficient transportation and city planning, limited land protection, limited investment in renewable energy and climate action, as well as an increase in population, an increase in agriculture, development and energy exports, and high levels of degradation and conversion of forested lands. So the NELFP, they can take the scenario narrative and they can model it to create this spatial representation of how these changes will impact our regional landscape. So from this project, we have these unique spatial outputs for all 5 of these scenarios that we can then use to estimate or map our species future distribution. So in order to estimate our species future distribution, rather than using our current conditions data like we did in chapter 1, we can use these scenario projected data for that region, and we can apply our model to those future conditions. And that allows us to estimate our species future distribution. So here what we're seeing is our distribution for American black bear, our example species. We're looking at what this species distribution will look like in the year 2060 if the New England landscape changes following a similar trajectory to that of the growing global scenario. So we can take our models and apply them to each of our future scenarios to generate these distribution maps relative to all of those different trajectories of change. So here we're looking at our current conditions map for black bear and these 5 different scenario projected distribution maps for that species. So the nice thing about these maps is they show us how much of our region will represent potentially good habitat, and where within the landscape we're likely to see favorable habitat conditions or high occurrence probabilities for these species. So these maps can be used for many different assessments. One which we are interested in is how distribution may change over the next 50 years. So to evaluate change, we can take our current conditions map and compare it against our scenario projected maps to estimate the degree of change in that distribution. So here we're seeing a change map for black bear, where those orange and red regions are areas of decline. So these are areas where our future habitat conditions are less favorable for that species, and we're seeing a lower likelihood of occurrence in those regions. And then the green regions are areas where we're seeing potentially improved habitat conditions and a higher occurrence probability in the future. So an increase potentially in occurrence within those regions. So this example is, again, for the growing global scenario, but we did estimate distribution change for all 5 of these future scenarios. In these maps, they provide us with this spatially explicit information about how each of these scenarios may impact our species distribution. So we developed maps like these for all 10 of our species, and this allowed us to look at trends in distribution change. So here we are looking at the percent of regional change between 2010 and 2060 on the y-axis, and then that's dispersed by species and scenario on the x-axis. And really, the main takeaway from this figure is that for most of our focal species, their distribution is expected to decline in the future. We're seeing most of these bars are on the negative side of this axis. And some of those species we're expecting to see pretty considerable decline. So under the Yankee cosmopolitan scenario, for example, with moose, we're seeing greater than a 60% decline in that species distribution. We do, however, see some variation among these scenarios. So looking at moose, again, we can see that while this scenario states a 60% decline, we can see that under goat alone, there's only a 20% decline. And that's a pretty big difference. So this is important information because understanding what scenarios and drivers may lead to these lower levels of decline or different changes in distribution, this can be helpful to inform conservation and management planning. So looking back at our scenario maps for black bear, so not only do these maps provide information about scenario-specific distribution change, this framework, it also provides us with an opportunity to isolate each of our primary drivers on this axis and evaluate how these drivers influence distribution change. So for example, if we want to isolate the influence of our global SEC driver, this driver here, we can take the 2 distribution change maps associated with that driver. We can take our global growing global scenario and our Yankee cosmopolitan scenario, and the maps associated with those drivers. And we can combine this information among these scenarios to marginalize the influence of the secondary drivers. So it would be marginalizing our low and our high drivers and really just targeting our global driver. We can also subtract the influence of changes that are expected under recent trends. And this again allows us to just target those changes that are specific to that driver, that global SEC driver. Subtracting our recent trends baseline, it also gives us a consistent baseline for comparing across all of our drivers. So we combine information across each of these axes to isolate changes associated with each of these primary drivers. And this allowed us to develop these driver-specific change maps. Each of these maps is showing you the isolated influence of that driver on distribution change for our focal species. And where these green regions are areas where the driver led to an increase in occurrence probability, and the purple regions are regions where we saw a driver led to a decrease in occurrence probability. So we also quantified these driver impacts for all 10 species. And this allowed us to compare impacts among our species and drivers. So this graph is showing us how drivers influence distribution change relative to recent trends. So our intersection between the X and Y axis, This is our recent trends baseline for each of our species. And each bar is showing you how that driver shifted distribution change from what is expected under recent trends, or under the recent trend scenario. So at a first glance, we see that most of these bars have positive values. And this means that we're seeing that these drivers improve the outlook for many of our wildlife species. So we're seeing higher regional occurrence than we are expected under recent trends associated with changes from these drivers. We can also see that different drivers have a greater influence on individual species. So if we look at our gray fox here, we can see that the low NRPI and our global SEC drivers, those have a much larger impact on that species distribution than our high NRPI and our local SEC drivers. So if we overlay this information, we can also look at trends for the focal group. So here we're looking at the relative effect of each of these drivers on distribution of change. And as we were seeing before, there is a lot of variability among our species and our drivers. However, we're seeing that there is a skew towards our global and our low natural resource planning. And this is because these two drivers had the strongest influence on distribution change for the largest subset of our focal group. We also compared the cumulative effect of NRP and SEC on our species distribution change. And we found that NRPI had the strongest cumulative impact on our focal group. However, we do see that the effect associated with SEC was also similar in strength. So we see that these aren't all that different. Really, overall, all of these results, they indicate that both natural resource planning and socioeconomic factors are influencing our wildlife species. And this highlights the importance of considering these factors when developing conservation and management plans, especially since changes associated with each of these drivers can improve the outlook for wildlife species in the future. So that brings us to the end of chapter 2. In this study, we mapped our species future distributions. We evaluated how alternative landscape futures impact distribution change, and we quantified and compared how two social drivers of landscape change influence distribution change in the future. So moving on to our third and final chapter, which is focused on wildlife resilience and protection here in the New England region. So this chapter is focused on three main objectives. The first is to assess distribution stability under our alternative landscape futures, and then use that information to identify areas where species are most resilient to future change. From that information, we can then evaluate trends in species spatial resilience and existing land protection throughout New England. So to conduct this assessment, we continued our collaboration with the New England Landscape Futures Project, and we built off the work we completed for chapters 1 and 2 to really evaluate patterns in species distribution stability and resilience throughout this region. So in order to evaluate distribution stability, we can use our current and future distribution maps, as well as our distribution change maps. And we can set thresholds within each of these figures here, and that allows us to isolate these areas of interest. So we can take our distribution maps and we can set a threshold to isolate areas that are only high occurrence. So what we're seeing here in red are areas where our species probability of occurrence is greater than 0.75. So we're seeing in these red regions that species is likely to occur in these locations. And then within our distribution change map, we can isolate areas of minimal change. So here what we're seeing in orange is areas where there was a very small change in distribution, or excuse me, in occurrence probability between 2010 and 2060. So we're seeing less than 0.05 shift in occurrence probability. So by combining this information, we can look at or isolate areas that are both high quality or high occurrence and resistant to change. And that's what we're seeing here in blue. We're looking at these areas that are likely to remain stable between 2010 and 2060, and we're seeing those high quality resistant areas in blue. So this process was completed for each of our future scenarios, giving us this information about species scenario-specific stability throughout New England. So these blue regions, they provide information about how these different trajectories of change will impact distribution stability. And collectively, we can use this information to evaluate species spatial resilience. So to evaluate resilience, we can combine this information to identify areas of consistency among our scenarios. There's a little bit of lag there, sorry. And these areas of consistent high occurrence are what we're seeing in green here. And these represent areas where species are most resilient despite uncertainty and future change. So we developed these resilience maps for all 10 species, providing us with this spatially explicit information about how species about species regional resilience. So again, these green regions are areas where our species are most resilient to future change. And then on this bar graph we're seeing here, this is showing you stats based on these maps. So we're seeing the percent of the New England region that is resilient for each species. So the percent of each of those maps that is covered in those green pixels. So what we see from these maps and this bar graph is that some of our species have high levels of regional resilience. So coyote or white-tailed deer, we're seeing that there's a lot of green in this map for those species, and that's leading to high levels of regional resilience. However, other species have very low levels of regional resilience. So species like moose, which we're actually seeing no resilient pixels within that map, and wild turkey, which have much fewer of those green pixels. We're seeing those are much lower levels of regional resilience. So for this study, not only were we interested in looking at species spatial resilience, we also wanted to evaluate relationships between resilience and our existing land protection. So to do that, I'm going to first give you just a little bit of information about New England's protected network. So New England has over 57,000 protected areas. The majority of these protected areas are under public ownership, are private lands with protective easements, or are owned by nonprofits like the Nature Conservancy. The size of individual PAs within this area, or within this region, they vary significantly. However, generally we see that northern New England has much larger parcels, so we're seeing that there's much larger collections of black up in these northern regions, and in the south we're seeing a lot of very small parcels. So overall, about 22% of this region is under some form of land protection. With these rapid changes occurring in this region and expected to continue, it's important to understand how our current protected network aligns with our species' future distribution and resilience. So to look at the overlap between resilience and protection, we compared our species resilience maps with a map of the region's protected areas. And then we identified these sites that are both resilient and protected for each species. And what we see here is an overlay for black bear, where these black regions are protected areas and these green regions are that species resilient pixels. And we see that about 9% of the New England region has an overlap between these black and green pixels. So given that 22% of the region is under protection, some of our species, including black bear, we're seeing pretty high levels of resilience within those protected areas. So we also wanted to look at how much of our species regional resilience was represented within the protected network. So here we're looking at the conditional probability of protection given a species resilience. Before we were looking at the region as a whole. Now we're looking at these areas in green. And we're saying, or asking how much of these resilient areas are also under protection. So for most of our species, we see that the protected network encompassed moderate levels of regional resilience. So if we look at our bar graph, we're seeing pretty moderate numbers. We're seeing between 13 and about 36% of resilient pixels for most species are also under protection. And this is a good thing. We're seeing that this is telling us that we're seeing alignment between these resilient areas and protection within this region and for these species. It's also worth noting that protected areas may be particularly important for the long-term resilience of species like wild turkey or gray fox, because we're seeing these higher proportion of their resilient cells are occurring within protected areas. And this suggests that resilience may be more reliant on protection for those species. We also looked at resilience from the perspective of the protected network. So we did this so we could look at how well represented or how poorly represented our species are within this network. So here we're looking at conditional probability of resilience given protection, and we're asking how much of these protected areas in black are resilient for each of these species. And we see that some species are pretty well represented, kind of the same species we've been talking about. We see that coyote, black bear, white-tailed deer, they have pretty high levels of representation within our protected network. However, other species like moose, white-tailed deer, red fox, they have pretty low levels of representation within this protected network. And in the context of conservation, knowing which of these species are already well represented within this protected network and which species may need further protection, this can be valuable information for potential future parcel selection or reserve planning. So the last thing we looked at was the collective resilience of our focal species within individual protected areas throughout this region. And what we found is that most protected parcels had generally low average focal species resilience. So here we see the number of parcels within the region on the y-axis, and that's distributed by average focal species resilience across the x-axis. And what we're seeing is the majority of the region, the majority of protected parcels in the region had resilience scores below 0.03. So what this means is that about 81% of our protected areas provide high levels of resilience protection for 3 or less of our focal species. We also see that no parcels were resilient for all 10 of our focal species. So we see that this this graph ends at 0.7, which means that at maximum, a single protected area only provided resilience protection for 7 species. We do also see that only a small portion of our region's protected areas provide resilience protection for at least half of our focal species. So only about 5% of the protected areas in this region are providing resilience protection for at least 5, 6, or 7 species in our focal group. So these results, they really highlight how important the network is rather than individual protected areas for conserving our wildlife species. Because what we're seeing here is these low levels of multi-species protection with individual parcels. However, different parcels throughout the network are providing high levels of resilience protection for different subsets of our focal species. And this is leading to many of our focal species having those moderate levels of representation within the network as a whole. So that brings us to the end of chapter 3. For this study, we assessed distribution stability under alternative futures. We identified resilient areas for our wildlife species, and we evaluated the overlap in species spatial resilience and our existing land protection here in New England. So to review all of this research, in this project, in these 3 studies, we first developed our species distribution models through expert elicitation and mixed modeling methods. We then used those models to generate these regional distribution maps relative to both current and scenario projected future conditions. And then we evaluated how different social and ecological drivers of landscape change influence distribution change for our wildlife species. We also then identified areas where species are likely resilient to future change and assessed how well the region's existing reserve network will protect our wildlife species in the future. Excuse me. So collectively, this research really demonstrates the utility of expert-derived SDMs, or species distribution models, as well as scenario planning for evaluating wildlife futures. It also advances our understanding of these key wildlife species here in the New England region. And potentially the most valuable contribution of this research is that it provides these novel tools and approaches that can be used by others to help inform more proactive and collaborative decision-making and conservation planning. So before I finish, I would like to acknowledge all of the collaborators and contributors of this work. This research was part of the USDA McIntyre Stennis program at the University of Vermont and wouldn't have been possible without the support and collaboration of USDA, UVM, and the Vermont Co-op Unit. I'd also like to acknowledge John Katz for all of his help with our AM survey platform, as well as Matthew Dovnick and Jonathan Thompson for their help and collaboration with the New England Landscape Futures Project. And also a huge thank you to all of the wildlife experts who took the time to participate in our wildlife survey. And then last, but definitely not least, I would like to acknowledge my committee members, Ruth Mickey and Tony D'Amato, as well as my advisors, Terry Donovan and Jed Murdoch. You have all been amazing resources and have provided instrumental guidance and encouragement throughout this process. So thank you, thank you, thank you for all of your help. So with that, thank you all for your time and thank you for joining us remotely. And I'm happy to answer anybody's questions.
Thank you, Skye. That was great. I'm gonna, if you have questions, please just put something in the chat and then we can call on you so that we're not bumping into each other here. So Erin has a question, and Erin, I'm going to unmute you and let you ask your question.
Great. Hi, Skye. Great job.
Thank you.
Yeah, I have a question about chapter 2. So you had these different projections for different scenarios for each species. And I noticed in that figure that some species, the projections were pretty similar across the scenarios, whereas some, I think the moose was quite a bit of variability. And I was wondering if you had ideas about what was driving whether those projections were, pretty consistent, say for the bear versus the moose, which is more variable.
Yeah, there's a lot of different things that are kind of going into those scenarios. So some of this, so for moose, we see a lot of variability for moose in particular because they are dependent on forest structure. And in some of these scenarios, timber harvest is a main thing that is changing. So for moose, we see if there's a lot more timber harvest, we're seeing that there's a lot more early successional or young forest, and that's causing that species to really improve its habitat conditions, basically. So it kind of just depends on what that species' particular requirements are and what's driving that model. And if one of those variables is changing a lot among our scenarios, then that's why we're seeing quite different impacts for that species distribution.
Awesome, thank you.
Of course.
Thank you. And Donna has her hand up. Donna, how did you put your hand up?
Can you hear me?
We can hear you.
All right. Well, first, I don't know. It says here to, that you can raise your hand. So I was getting ready to type my question. Anyway, first of all, Skye, that was a great presentation. I think it was so well organized, and I know that this is not the format you were hoping for, but I just want to say what a great job you did with that. And so this may sound like a stupid question because that's the ones I usually have. But I just really wonder, given the really poor prognosis on moose in Vermont or New England, I mean, what do you think management agencies should do? Just quit trying to do anything?
Oh man, no. It's so the thing that these scenarios are showing you is that we're seeing, like, especially for moose, we're seeing that there's a lot of different changes. So this could provide information to management agencies to show you like what scenario is leading to the lowest level of decline and what's really driving, what's driving that scenario. So if we're seeing that we can increase early successional habitat for that species and that's helping, then that's, that's valuable information. But also a big thing for species like moose is our climate shifts within our scenarios. So it may not be valuable to invest in things like habitat within our southern regions, particularly for moose, because we're seeing that the climate shift is probably going to, reduce that species distribution in those regions no matter what. So it can help kind of show you the spatial regions and where you might want to target conservation and management, as well as how to potentially tailor that management to be most successful.
Okay, thank you. That makes sense.
Yeah.
Okay, great. Thanks for that question, Don. I'm just going to read a note here from John Cart. John says, Sky, thank you for your efforts. Organizing the ologists is no easy feat.
It wasn't.
Matthew has a question for you. Matthew, I'll unmute you as well.
Great job again. Terrific.
Thank you.
Nice figures, especially. So I've been thinking about the protected areas in your last chapter, and I'm in the middle of reviewing that manuscript. And those protected areas, they come in lots of different flavors, you know, with and without timber harvesting allowed, close or far away from roads or people, edge habitat, some have early sterile habitat, et cetera. And what do you think, what aspects of those protected parcels do you think will be most important to your species? Again, this is sort of more of a outside of your dissertation kind of a question, but I'm just curious, what your thoughts are. What would make those protected areas more or less valuable, given that they really do vary substantially?
Yeah, that's a hard question to answer because our species have such different habitat requirements. And I think I ran into this a lot throughout this research. It's hard to make any sort of recommendation with this focal group because they're such different species. And so I think it kind of just depends on your objectives, right? So if you were targeting a certain species, you would be able to, or a certain group of species, it might be easier to understand what parcels or what we should recommend in terms of parcel selection. And I think that's kind of the goal of this work, is to provide those tools that can help others that have certain objectives address those objectives. But it's a hard question. I think what the point that kind of got hammered into my head is really more the importance of the network than just those individual parcels. So I think it's kind of like knowing what else is around and what else is there that can be just as useful as the individual parcel itself.
Yeah.
I don't know if that really answers your question.
Yeah, no, it does. It's an interesting question and interesting.
It is. It's a good question.
Well explained. Thank you.
Yeah.
Well, thank you for that question, Matthew. Josh, did you have a question? Oop, hello, Josh. I think, hang on a second. I think I might have unmuted you and you might have pushed the button at the same time, so we canceled each other out.
Oh, can you hear me?
Yep, yes. We can hear you.
Oh, perfect. That was wonderful, Sky. Thank you for that. And I guess I was just wondering, just as a kind of a broad question, which I think kind of goes with John Cart's as well, was how you might think about how some species, like a black bear or a raccoon, may be better able to adjust their behaviors to coexist with human development. So although experts may not see currently suburban areas as really suitable habitat for a black bear, will they be able to continue to utilize those areas, and how you might kind of include that adaptability into a model like this?
Yeah, that's a great question. At this point, these are kind of static models. They're just based on the data we originally collected, but we could incorporate that information. These models could be kind of a base of a Bayesian framework, and you could add more information as we get new data, or we understand that the species are adapting to different changes. That information could be incorporated into these models and kind of create an updated model that you can then use in the same framework to make these projections. So it's not currently incorporated because this is based off of these current conditions, but it could be in the future.
Great. Well, thank you very much. It was a great presentation.
Thank you.
And John Cart, did you have anything you wanted to add to that?
just interesting to start thinking about this, these changes in such a coherent way. So I really appreciate your work, Sky.
Thank you. I'm having a hard time hearing you. I'm not sure if you had to ask the question, but if you just said thank you, then thank you for listening.
He said thank you for presenting this information in such a coherent way.
Oh yeah, of course. It's the goal.
Okay, any other questions? You can raise your hand or you can chat it, and we have a couple of minutes if anybody else has a question. And while we're waiting, I'll just say what happens in these defenses is that after this public seminar is finished, then Sky will do a private defense with her committee, in which the committee asks more follow-up questions, and that would actually conclude the defense then. Jed, would you have anything you wanted to add to this at all before we wrap up?
No, I have some additional questions, but we'll hold those to the defense. Great job, Sky.
Thank you.
Matthew says, good luck with the defense step from Amy. Matthew says, I can another. I'm not sure.
I'm sorry. I can ask another. I have another question.
Go for it.
Just on the, back to that discussion about moose and the large declines. I guess that's maybe just the point that there's a real trade-off in those scenarios, in that the decline in, for example, timber harvesting in the Yankee cosmopolitan, that immediately looks like, oh, this is great, you know, there's a lot more carbon on the landscape. And so a lot of the stories having to do with these scenarios have been, we've discussed the carbon, but indeed there is a trade-off in that we're creating less, I don't know what is driving that moose decline, if it's sort of lack of early seral habitat, or what, but this just points, your work really points out the value in looking at sort of multiple angles or multiple ecosystem services from these scenarios, and that there was, that they're not always linear or straightforward. And I don't know if you want to comment on that, or any other surprises that you found in your results.
Yeah, I think that a lot of the surprises were kind of like at first glance, just like natural resource planning and innovation. You hear that term and you're like, oh, high natural resource planning and innovation is going to be good for wildlife. Like that's just kind of, I think, what most people would hear and think. But it's not necessarily true, because it really depends on what you're investing in within that, right? So if we're investing in different ways of like doing timber harvest or conservation, that means that we're doing different practices within different regions. And those might not have targeted a specific species, so they might have negative impacts. So it is really interesting to kind of see how a project that wasn't targeting wildlife explicitly, how those projections are impacting those species, because they're not necessarily what you might expect.
Right. Well, fantastic. Good luck on the next hour.
Thanks.
All right, Matthew, I think you had the last question. Yeah, I think now we will close out and say thank you to all of you for joining us today. Thanks to Sky for a great seminar, and you'll be hearing from Sky soon. So